Hello. I would like to show you how to do limiting reactant and percent yield so that you can get a better understanding from what I've posted so far with the introduction of the CK12 lessons and the simulation and some of the narrated notes that I've provided. So first of all, we're going to have to start off with a balanced equation. So we have antimony reacts with iodine to form antimony triiodide. So antimony reacts with, and iodine is one of those diatomics, to form antimony triiodide. So I have 1 and 1 antimonies, but 2 and 3. So 2 and 3 are factors of 6. So I'll have 2 antimony triiodides, and I'm going to need 6 iodines and then 2 antimonies. So I know that my coefficients can be not just atoms and molecules, but then they also tell me the moles. So I can have mole ratios of things, okay, which is going to allow us to convert between A and B of things. All right. Question is, which reactant is limiting reactant if we have 1.2 grams of antimony and 2.4 grams of iodine? And we need to find the percent yield that was if 2.5 grams was actually recovered in the lab. Okay. So since we're given mass and not moles, and we're going to have to calculate mass for the theoretical yield anyway in order to calculate percent yield, we're going to go ahead and convert mass of antimony to mass of antimony triiodide, and we're going to convert mass of iodine to mass of antimony triiodide, and then we're going to compare those two masses to find out which one limit the product produced, and that's our limiting reactant, which will give us our theoretical yield, which will allow us to calculate percent yield. Now, if you were given moles here, you could just simply use the mole ratios and convert moles of those and compare moles, and then you would still have to convert those moles to mass in order to do the percent yield. Okay? So I'm going to start off with my 1.20 grams of antimony. I know that 1 mole of antimony from the periodic table is 121.75 grams. Well, that converts my mass of antimony to moles of antimony, which is my substance A, and I need to convert to substance B. So I'm going to need the mole-to-mole ratio, which is 2 to 2, which happens to be 1 to 1. So I'm converting 2, literally T-O-N-T-W-O, 2 moles of antimony triiodide from moles of antimony. And now I'm left with moles of antimony, but I need to convert moles of B to mass of B, again using the molar mass. So 1 antimony, 3 iodines gives me 504.65, sorry. 65 grams of antimony triiodide for every 1 mole. So in the calculator, I would do 1.2, this is 1, times 504.456 divided by the mass of antimony. And I get a final rounded answer of 4.95 grams of antimony triiodide. Okay. Now we're going to have to do the same thing with the iodine. So I need to convert mass of iodine to moles of iodine. So from the periodic table, I see that 2 iodines added together gives me 253.81 grams of iodine. And I see from the mole-to-mole ratio, I produce 2 moles of antimony triiodide. for every 3 moles iodine that reacts. And now I need to convert, just like I did here, moles to mass using the atomic weights of antimony and iodine. And in the calculator, 2.4 times 2 times 504.465 divided by the product of the mass of iodine and the moles of iodine. And I get a final rounded answer of 3.17 grams of antimony triiodide. So when we compare these masses, I see that iodine produced the least amount of the mass. Okay? Therefore, iodine is the limiting reactant. Okay? And therefore, antimony is the excess reactant. It means there's going to be some antimony left over that doesn't react. And we don't indicate it in the balanced equation. We just only look at the things that are involved in the final product. Okay? So now that I know that this is my theoretical yield, I can now calculate my percent yield. Okay? So the percent yield, I guess I'll do it right here, because I want to also do excess reactant. And we were given the actual yield, and then we put that in the calculator, and we get 78%. So not a good yield, because we want close to 100, although not all reactions will go to 100. But if you're working in manufacturing or in pharmaceuticals, you're trying to calculate for the things you put in for the product you want to make, you're trying to get as close to 100% as possible. Okay? Otherwise, your productivity is not very good. All right? So it's not in the problem, but I would like to go ahead and show you this. How much of the excess reactant reacted and how much was left over? That's easy to do, because you can take the limiting reactant and find out how much mass it reacted with. Okay, and that mole to mole ratio is 2 to 3. And we already know the molar mass of antimony. Okay, so cancel our grams and moles. And then our final rounded answer happens to be 0.76 grams of antimony reacted with the 2.4 grams of iodine. Okay, and then how much was left over? Well, you take the 1.2 and we get, oh, I calculated that wrong, hold on. Okay. So this allows us to figure out how much of the excess reacted and then we can also find out how much of the excess reactant was left over. Okay, and again, this we could have been given moles here. If we were given moles here, then you would have just done the moles to the mole ratio and then compare the moles, and then you still would have had to make this last conversion to figure out. Once you figure out the mole difference, then you can still do your mass to find out this, and then you could do the percent yield. And then if you happen to be given, you know, how many, or it could have been said in moles, you know, what's the limiting reactant in moles, you know, or we could have said, you know, how much, and you'd still have to convert to mass even if you were given moles. So it's always just easier to given moles, find moles, or given mass, find mass. So either one of those. Okay. So hopefully this helped. And then I'm only going to do one of these to make this short because it's 10 minutes. Okay? And if you need another example, let me know.